Pretty cool. So, yeah, so it's a great pleasure to have Cesar Galindo speaking to us today from Hamburg. He's at the University of the Andes in Colombia. So he's going to tell us about braided zesting and its applications. And if you have questions, you should just unmute yourself, and Cesar, be prepared for interruptions if necessary. Yeah.
Perfect.
So go right ahead.
It will be great. I mean, please ask, and yes, we'll be happy to do it. Okay, thank you very much for the invitation. It's an honor for me to be here. So I want to talk. It's my second time with Zoom, so please be patient because I will do the typical mistake all the time. How I can, yeah. Okay, so the talk that I will present is based on a recent paper with Colleen Delaney, Julia Plagnick, Eric Rowell, and Xin Chang. This is it's already in archive. Yeah, and the idea of the paper, or what we did, was the following. We developed, I mean, a technique for the construction of braided fusion categories, changing a little bit the fusion rules. So the idea, as I will explain later, is that we will change the fusion rules using a Tuco cycle, a group Tuco cycle. I mean, this technique was used previously, and I will talk a little later about that, but it was used, for example, for the construction of modular, supermodular categories, and also for the construction of some, let's say, a strange modular category that we found when we were classifying modular categories of dimension 36. Okay, so
Cesar, I already have a question.
Yes, please.
So, you know, when you have a two-code cycle, in the process of gauging, you can use that to change a G-cross braided category.
Yes.
Would be that the same thing? You just do it as a G-cross category, and then you try to understand if the obstruction, you know, for fusion and braiding. Well, I think actually fusion is already there. It's just a question of to trivialize the obstruction.
Exactly.
Braided from G-cross braided to braided.
Yes. Yes, okay. The point is the following, but I will try to answer better for everyone later. Okay. But I can say the following right now. When you use this Tuco cycle, I mean, what you will get is a G-cross braided category.
Yes.
In general, this G-cross braided category, in order to be again braided, you need a trivialization of the action. So in some sense, what we are doing here is picking Tuco cycle and some other extra data in order that this, in order to fix a trivialization of the action of the G-cross, of the new G-cross braided category associated.
Okay.
Yeah, so you are completely right. I mean, that's exactly what we are doing. But let's try to do, I mean, I want to perhaps talk about that later.
Okay, thanks.
Okay, so the first thing is I will start fixing some notations for the Grotten, the ring, or the fusion rules or of my fusion category. Just, I mean, I want to recall some things just in order to fix notation. So if you have a fusion category, I will denote by I just the set of equivalent classes of simple objects. So because this is a fusion category, this is just a finite set. And also, if you have two simple objects and you do the tensor product again decomposes as a sum over some simple object with some multiplicities. These multiplicities, in terms of the fusion category, are just the dimension of the home spaces from C to A tensor B. So they are just the multiplicity of, let's say, C inside of this tensor product. So the fusion rules are exactly that, no? So it's a finite set well, it's a little more, but for this, it's a finite set with some non-negative integers, such that this product defines an associative algebra over the free abelian group generated by the set I. Well, in addition, we need an involution of in this set, but just to fix notation, this is the only thing that I need at this moment. Okay, so we have a set of fusion rules. This is the first thing that I need right now. And let me start giving an example, because I want to present all the results with a concrete example. That's the idea, not just to present the theorems, but also a concrete example that is quite interesting. It was one of our motivations for the paper. So the example where we worked with a lot of details was SUN level K. So by SUN level K, I mean the following. I mean the fusion, really it's a modular category, but at this moment, I mean only the fusion category that you can construct from the quantum group associated with FLN in Q equal to a root of the unit of order 2L, where L is N plus K. So the level, this K, it's associated with this L through this equation, okay? So that's the connection between this category that, for example, in the book of Bakalov-Kirillov appeared, and this notation of SUN level K. So what are the simples? Well, the simples can be, let's say, labeled by two different sets of things. One, it's we can label by n non-negative integers such that the sum it's exactly k, or you can label also by partitions. By partitions, I mean a set of numbers, non-integer numbers, again, non-negative numbers in this way. And if you have a partition, I mean, you need some conditions here. The condition is that, I mean, this is a partition, so you have here a decreasing, and here you have really m numbers different to 0. So I need that this m should be less than n, and also I need that the first number has to be less than equal to k. So you also can put this information in a Young diagram, and these conditions mean that your Young diagram fits in an n-1 k rectangle. And the formula to go from one of this sequence to one of this partition is very simple. I mean, I wrote down here, if you have n numbers that the sum is k, then the partition associated is this one. And conversely, if you have one partition, then you can associate one partition with these conditions, then you can associate the sequence in this way. The idea is that this sequence will be associated with the linear combination. I mean, because in general, the representations of this, the simple representation of this category are associated with some weights associated, I mean, when you can describe using a weight lattice associated with elements in some weight lattice. So this is let's say the coefficients when you use the fundamental weights. So that's, I mean, there is another way also to present exactly the same information. As a concrete example, but this is one of the...
Yeah. Question.
Yes.
So I think, roughly what it is that when you represent a simple object by the Young diagram, you take the dual particle, all you need to do is to take the diagonal and then flip it. But it's not always true. So what you need to do if, you get a illegal diagram, you know what I mean? if you take the second way of representing a simple object, and I'm asking, how do you figure out the Young diagram for the dual?
Oh, yeah. No. Yeah.
I guess it just take the diagonal flip, but it's not always possible.
No. It is not. No, in general, even this diagram, yeah, I think. I'm not completely sure.
That flip diagonal.
Yeah. I don't know, to be honest. I mean, what is the?
It's an interesting combinatorial question.
Yeah. I haven't thought about that. Yes. Yeah. It's a good question. Even I don't know exactly the description right now.
Well, that one's more complicated. That's a bad way to represent, but I think the Young diagram has to be related to take the diagonal and then flip the row and column. But this constraint is not preserved, so there must be some reflection.
Yeah.
So the usual thing for, like, if you have a written in terms of diagram, in terms of the vector, you turn it around, basically. You flip end to end.
Okay, I
That's
think
duality.
you have to flip, then do some reflection, to make.
Look, for example, this in this case, I mean, this 003 corresponds to the empty Young diagram, and so on. But this corresponds to an invertible element. For example, this corresponds to the fundamental weight with 3 times the first fundamental weight, and the dual of this is this one.
Okay, so more complicated.
So it looks quite different if you see. I mean, this is the dual of this, and this is the dual of this.
Okay.
Yeah, so it's not clear immediately how is the connection.
But there must be an algorithm, so.
Yeah, should, of course, and yeah, of course, because it is not so complicated, but I at this moment I don't know exactly the rule for the dual.
Find a high school student, ask him to do it.
Yeah, I have a question here.
Yes.
For the lambda description, looks like lambda equal to 0 will be okay. All lambda equal to 0 will be allowed.
All lambda equal to 0, it's allowed.
It's not ruled by your constraint.
Yes, this corresponds to what I call the all lambda equal.
The reason is that if lambda all equal to 0, then that means A all equal to 0. Then this
but by definition, when a partition means that this number should be bigger than 0. I mean, if you put 0, then it corresponds by definition to the empty partition. So that's what I call here empty.
I see. But so, for example, if all lambda equal to 1, if all lambda equal to 1, it's incompatible with the sum of A equal to K. That's my question. Here, sum of AI equal to K, and you can choose all lambda equal to 1 below certain m. Then that's then K can be large. Then sum of A can be very small. So I'm a little bit confused.
Oh yeah, I think there's a mistake somewhere. So look at the left-hand side. If summation AI equals K, that means lambda 1 minus lambda n equals K. Because look at the translation.
Yeah.
Yes.
So, but the constraint on the right-hand side is not lambda 1 minus lambda n equals K. So there's something not quite right.
Oh.
Because what you are saying, the change of label is AI is lambda I minus lambda I plus 1. If you sum them all up, then summation AI equals K means lambda 1 minus lambda n equals K.
Yes.
Maybe there's some constraint on lambdas. There's some additional constraint on lambda.
I mean, the constraint of lambdas are the following. But if I remember correctly, it's just n should be less than n.
Or maybe sum over AI not equal to K. In your example, you can see this 101. Sum of 101 equal to 2, not equal to K.
Yeah, maybe this should be maybe it should be less
less equal than K maybe. Sum of AI is less equal than K.
No, that's also not correct because it's
equal to K.
Maybe the translation is not correct. I don't know.
No, I think the inverse map, the formula is different in the last spot. So if you look at lambda 1 minus lambda 2 minus lambda 3, and all the way the last one for an, that's not something like a lambda n minus 1 minus lambda n. It's not that. I think it's
there's some choice.
It's k minus something.
Yeah, you're right. Okay,
here summation AI should be less or equal than K.
Last point, there is something a little different. You're right.
Yeah, okay. Then that should be not equal K. It should be less or equal than K.
Yes.
It should be consistent.
Yes. I mean, this formula, it's a very well-known formula. I extract, but I copy very quickly. But yes, it's something very, very well-known. Yeah, but yeah.
Okay, I think the last spot should be K minus lambda 1. Maybe something like that.
Yeah, in order to have the sum, the sum equal to. Thank you. Yeah, but at least for these examples, I double check, so I think it's correct.
But there's also a problem. Sorry, there's a 101. There's a 101.
Yeah.
Sum of 101 is equal to 2, not equal to 3.
I think that should be changed to less or equal than K.
Yeah, this is 101.
Yeah. I think the summation
I wrote so quickly. So it's 1. This is 102.
Oh, okay. That's
102.
Better.
Yes. This is 102, and in that case will be fine. It's 102.
Okay. Great. Thank you.
Yeah. I'm completely sure that this is one, because the box that corresponds exactly, I mean, one box exactly corresponds to the standard representation, and the standard representation is exactly the first fundamental weight, so it corresponds exactly here to 1. One other way to think about that is to have a n minus 1 numbers such that the sum is less than equal to K. So in some, this is, I apologize, but thank you. Yes, here is 2. I'm sure. Okay. Well, but even if you have the labels, one thing that is not straightforward at all is to say what exactly are the fusion rules. Something that is easier is to say what is the fusion graph of the fundamental representation. And in some cases, with that information, that is enough to describe the whole fusion rules. I mean, all other elements. So what I mean by the fundamental representation is the representation or the simple object associated with 1 square that correspond exactly to take, let's say, 1 fundamental weight. And in this case, I mean, I learned this formula from a paper of Alan Bourgier, but in this case, there is a concrete formula in terms of the Young diagrams to describe the multiplicities. I mean, the fusion graph is the direct graph with labels, the simple objects, with ages given by these numbers. Yes. So here, this is the x. So here, for example, for the case of SU2 level K, some people call this the AK fusion rules, exactly, because when you look the fusion graph, the graph that you get is this one. Well, really it's a direct graph. So here you should have some others, but yeah. And here also for SU3 level 3, the fusion graph is given by this. I mean, something like this, where this green dot corresponds to the standard representation. Well, one of the things that we need in order to do testing is a grading over the fusion rules, or a grading over your fusion category. So a grading is the following. It's to assign a label to every simple object. I mean, you start with a finite group, okay? So you have a group, and then you have to assign to every simple object an element in your group. And it should be compatible with the fusion rules in the following sense. If you know that this number is different from 0, that means that if you take one simple object with A and one simple object B and you fuse them, then appears some C, and the grading, so the element of your group associated with this C should be the grading, I mean, this element should be the product of the gradings. So that means that the product will appear in the component associated with the product of the group. For example, SUN level K is set and graded. And the grading can be described as the number of boxes in the Xiao-Gang diagram. That's one way to describe it. So, what happened? So for example, here, this simple object, in this case, will have grading 0. This, again, I mean, in this case is 6, the number of boxes. 6 mod 3 will be 0, so it also has grading 0. This also has 3 boxes, so again it has grading 0. And yeah, grading 1, 1, 0. Yeah, there is, yeah. Okay. And finally, just to present the definition of abelian anions, sorry, the definition of Zesting, I need the notion of invertible objects. So the invertible objects will be the simple objects such that when you apply a tensor with the dual, you get the identity of isomorphic to the identity. So this subset of I will be a group using this product. And the inverse, of course, will be exactly a dual. So for example, in the case of SUN level K, the invertibles will form a cyclic group of order n, and the generator will be given by the simple object associated with the Xiao-Gang diagram of K boxes. That corresponds exactly with in terms of the weights to this one, to K times the fundamental, the first fundamental weight. Also, if you have a simple object, let's say, for example, this G, and you apply the tensor product with any other possible simple object, your tensor product will be again simple. So you have an action of this group on the set of simple objects. So for example, for this particular case, because this group will have, I mean, for this particular case, if you take one simple object labeled not in terms of Xiao-Gang diagrams, but labeled in terms of one tuple that sums K, then to do the tensor product of this invertible element, the action, I mean the new simple will be this one. I mean the action, I mean the cyclic action is given here. So it's in some sense very easy to describe. In particular, this is a way to describe what happened with the powers of this cyclic group. So now I can present the notion of associative testing. So an associative testing will consist of the following. So first, you fix a group G and a gradient. So a gradient, again, it's a surjective map that goes from here to here. And in addition, you need a Tuco cycle. And here, by a Tuco cycle, but a Tuco cycle that takes value in the invertible objects graded by the unit. I mean, trivially graded if you want. So, oh, yeah. And by Tuco cycle, I mean that it should satisfy this equation. And additionally, we need a map that goes from 3 copies of your group G to a complex number. And we will represent this number because as a morphism, because really that is what, really it's a morphism from the tensor product of, look, this one, oh, I make, yeah, 2 cocycles, so here, and that one. Yeah, so from the tensor product, so from this should be in the other side, but it's more or less the same, to here it should be lambda of G2, G3, lambda G1, G2, G3. So it's a morphism from here to here, but because this is a simple object, the tensor product will be again a simple object. Here again will be a simple object. So we can assume that a morphism from here to here really is just an scalar. So that is exactly this scalar that we are presenting here.
So Cesar's notation,
yes.
You use lambda for both map. Are they related or they are different?
Yeah, they are different. This is, yes. So the notation that I will use will be the following. The 2 cocycle has only 2 enters. Okay. So, and the 3 cocycle, this other function that has 3, even when it has the same letter, it has 3, I mean, it's associated with 3 different elements. So it will be a scalar. So it's a little different.
Okay.
Yeah.
They are not related.
They are not related. Yes, exactly. I mean, ones take values in the invertible elements with degree 0 or degree the identity of your group, and the other one takes values in the complex numbers and in the invertible complex numbers.
Okay.
Yeah. And now these 2 data should satisfy the following equation. This equation here. And this is written using graphical calculus. So the idea here is that this corresponds to lambda of G1, G2. This corresponds to lambda of G1, G2, G3, and so on. So look that, I mean, in order to really, this is an equation that is just scalars. I mean, at the end, this is just some numbers. Of course, to do an interpretation of this equation, really you have to apply associativity in general. So in general, you have like parentheses here, you apply this scalar, then you have to move the parentheses, apply this scalar, then move the parentheses again, apply this scalar. This should be the same as move the parentheses, apply this scalar, apply the braided here, move the parentheses, and so on. Yeah, but at the end, this is just some equation that you can put in terms of numbers associated with 4 elements in your group.
So this is a constraint on the 2 cocycle. It's not a constraint on the 3 variable. Which?
Yeah, it uses both, because here when I am putting here 1, 2, here yeah. I mean lambda of G1, G2. Here yeah. I mean lambda of G. So it's a mix. It's something that mix this 2 cocycle with this let's say 3 cochain.
Oh, I see. So the notation, the top 3 are 3 elements in G.
Yeah, so, look, here is the idea of the notation. When I write 1, 2, I mean lambda of G1, G2.
Okay.
When I write 1, 2, 3, I mean lambda of G1, G2, comma, G3.
Oh, okay. I see I see the notation. So in the middle, there are three numbers. There are three things, so that there's a scalar. Okay. I saw. Okay. Thanks.
Yeah. So
I have a question. So in your two lines, this two co-cycle plus this gradient, that's already guaranteed the fusion rule. So you'll get a consistent fusion rule from first two line. Okay.
Yes.
So the last line is associated with this F symbol or R symbol. So this will be consist condition to get a correct F symbol or R symbol.
Exactly. That's the idea. I mean, the next.
So what is that's F symbol or R symbol or both?
Sorry?
So whether this is a consistent condition is for F symbol or for R symbol or for both.
No. Will be only for F symbol. This rule of consistency will be for the F symbol. Later, we will see. Yeah, only for F. And as we will see later, the consistency of this doesn't imply at all the consistency of the R.
Okay, thank you.
Yeah. Mm-hmm. Okay.
And so, also, Cesar.
Yes.
And why? Sorry, could you go back to the previous slide? Is there a reason why you choose the braiding instead of the inverse braiding?
No, you're completely right. I mean, I can do any of them, but I have to be consistent later with the definition of the associativity. I mean, if I fix this one, then in the next one I have to change the associativity. So I have to be consistent with the following formula. In the next proposition, I will define a new fusion rules and also a new associativity. And the idea is that you are completely right. I mean, here I'm using, let's say, the inverse of the braid, no? But the thing is, will be some relation. Let me show you the next slide, and you will see.
Okay. Sorry, I have a question also. In the last slides, I'm sorry.
Okay.
So in your relation, you're involving a braiding. Whether there is a condition which do not involve braiding, since this is only for the fusion rule, only for the F symbol. Whether
I'm sorry. I forgot to say that I am starting with a braided fusion category.
Okay, I see.
I am starting with a braided fusion category. In fact, we did for a little more general, but in order to don't be, too technical at this moment, I prefer just to talk in terms of braided fusion category. So I am talking here with a braided fusion category. I'm starting with a braided fusion category. Some things that will imply this is that this G will be an abelian group, in fact. But this thing will have more sense in a more general setting, but also more things has to be included. So I prefer just to present it this way, just to do things a little simpler at this moment.
Okay, thank you.
So yes, here I can use the other braiding, and it doesn't matter too much, but the point is the following. The point is that suppose that you have, again, grading, one of these associative testing, then you can define a new fusion rules in the following sense. If you have a simple object labeled by G1 and you have another simple object W labeled by G2, then the new product will be just the old product of the first with the second, and then you have to twist by this value in the, by this simple in the two co-cycle. Here is when you need the braid, really. Because if you try to do the associativity, look here, you really need to braid things in order to get you need the braid in some moments in order to change, but the point here is that using this formula, you get a new associativity. So you get a new F matrix if you want. Yes. This is using graphical calculus, but of course from this picture, we can extract also a concrete formula of the new F matrices in terms of the old F matrices and the lambda and the both lambdas. Yeah, so it's a concrete thing that we can also do. The important thing here is that giving one associative testing, you can construct a new fusion category, changing this one. Okay, so here appears a natural question. Suppose that you only have a 2 co-cycle, because in general, 2 co-cycles are really easy to compute. One natural question is when there is some of these 3 co-change in such a way that you get an associative testing. And here, this is related with some work. I mean, the thing is you can define a 4 co-cycle that looks the obstruction to the existence of this braided testing. And this is related with a previous work of Pavel Ettingel, Dmitry Nikchich, and Victor Ostrich. So, but in this case, because I mean, the idea here is that we are changing from a G-graded fusion category to another G-graded fusion category. So we already know that this theory it's inside of this general theory of graded fusion categories. But one of the things that we did was to describe explicitly the abstraction just in terms of the 2 co-cycle. So in terms of the 2 co-cycle, you can construct this 4 co-cycle. Now, recently I realized that this 4 co-cycle was already known for some physicists because this corresponds exactly to the 4th obstruction when you study G-cross braided categories, when there is no, when the action doesn't permute the simple objects. So it's exactly the same 4 co-cycle that you obtain using these ideas. So in this case, the idea is that this formula will define exactly a 4 co-cycle, and the cohomology class of this 4 co-cycle will be the abstraction. In other words, if this abstraction if this cohomology doesn't vanish, then it's not possible to get any 3 co-chain such that you obtain an associative testing from these 2 co-cycles. And it's known some concrete examples where this happens. Okay, I want to describe associative testings of SUN. One of the things that we did was to...
I have a question for last slide.
Yes.
Even the previous, just one previous slide,
In this one?
Oh, the previous one,
this one.
Yeah. So
yes.
Here we'll define this twisted fusion, twisted by this 2 co-cycle. Okay. And so this lambda take a value in the pointed simple object.
Yeah, in the simple object graded in the trivial component.
Yeah. So So my question is following: whether this formula can be generalized even without a G grading. You just find some function lambda G1, G2, lambda VW. You find some lambda VW, and then just maybe there's some proper function. Then this modified fusion rule would work. So so my question is that whether to get a consistent fusion rule is always coming from this way. You have a G grading, you have a 2 co-cycle, then you get a consistent twisted fusion rule, or whether this can be generalized. So even without G grading, you can get a more just some way to get another fusion rule. Whether there's some study in this direction.
Yeah, well, the only thing that for me, it's more or less clear at this moment is that in some sense, it's not absolutely necessary here to be invertible. Well, it is, but when in some sense, when I try to see the pentagon equation, when we try to see the pentagon equation, I mean, really, to be an invertible object is not really important. But however, it's not clear for us if this object is not invertible, if this map will be an isomorphism. So it's possible to have some kind of, let's say, F matrices, but some of them, perhaps they are not invertible. This is one thing that I can say in that direction.
But my question is whether one can remove group grading, with the G grading, whether G grading can be removed to get some more general.
Yes, well, I mean, I'm just speculating, but you can grade your category not just by a group. You can grade by how it's called, by
maybe higher group or even something even more general.
yes. For example, for other fusion rules, yes, there are some other ways to grade for something a little more general. But we haven't, I mean, explored these other possibilities. It's something interesting. Yeah, but yeah, one of the things that also we were very interested in this case is because we really can do computations. And yes.
Yeah, this one can be programmed. We can check at least.
Probably. Cesar, I have a follow-up on the whole discussion. So what's wrong? What's wrong if you just write down the same formula instead of, you require lambda G1, G2P to be in the identity component? What's wrong is just, to be any simple object rather than just those either trivial grading? You know what I mean? Your co-cycle is not the most general. The two co-cycle engaging, you don't need to be inside the trivial sector.
No. Yes, you need, because engaging, what you are doing is only working with the trivial.
Oh, that's true. Engaging is in the trivial because that's by definition. But,
yes.
But what's wrong if I just, let to be a co-cycle for any simple object rather than?
The thing is the grading will change and we don't have then, I mean, perhaps it's possible to do it.
I know you want to, the action is a pretty kind of a boring. You take a simple object, you acting on one, and you never move out of the grading. That's why you want this to be the trivial, sector, right?
Exactly, because yes, exactly. The grading, I mean, yes, exactly. And the grading in particular won't change. Here, the grading of this one, the grading of this one will be again G1, G2.
Exactly, you don't change it. So I just ask us, a easier generalization. Just, get out of this, maybe you can change sectors. But anyway, so
this is something short to explore later. But
this is easier than Xiao-Gang wanted.
Yes. Thank you. Okay, so here is the fourth cycle. Okay, I want to, I mean, the following statement is not exactly in the same way in our paper, but it can be deduced, I mean, following all things that we did. But I want to talk a little about something that I don't want to present right now because it involves many things. But in the paper, one of the things that we did was to classify all possible zestings in the case of a cyclic group. And we did it in some sense because we know very well the cohomology of cyclic groups. And I mean, we can compute easily, not only to know that the H4 obstruction vanished, because this is something very easy from the standard cohomology, but also we can explicitly compute, let's say, coboundaries for the cocycle. So at the end, we have explicit formulas for all possible zestings in the case of cyclic groups. It was one of the things that we did, but it needs some things in order to present. So I decided just to present in the case of SUN level K, just to see with a concrete example. So suppose that, and this is part of the master thesis of one of my students. Okay, so suppose that you have this N and this K. We will define this epsilon. This is a particular case of something more general that we define in the paper as 1 if the GCD between N and K is even, and N divided the GCD and K divided this GCD are odd, and 0 otherwise. Okay, so it's just a number associated with N and K that can take 1 or 0 depending on this rule. So the thing is, the equivalent classes, this is something also that I didn't define, but there is a natural notion of equivalent associate, I mean, of equivalence zestings. But equivalent classes of associative zestings are parameterized by just pairs of numbers. Here it is set mod n divide the GCD of nk and set mod n. Okay, for example, in the case of SU3 level 3, this of course will be just 1. So the equivalent classes will be parameterized by elements in set 3 times set 3. And in general, this is, but we have explicit formulas for the Tuco cycle. The Tuco cycle is given by this concrete formula. Here I am, yes, so remember that for SUN level K, this is graded by set N. Okay, so I'm referring to this grading, to the canonical gradient associated with SUN level K, that is related with the number of boxes. Okay, and here this is the three cochain, and the three cochain here is where this epsilon appear. I mean, it will change a little bit depending of if yes, of this condition or not. And here, yes. And here by I, J, and L, I mean numbers between 0 and less than n. So they are very, very concrete. Okay, now let's go to braided testing. So we not only want to have a fusion category, we want to have also a braided category again. So I need to remember this thing. So I will denote by out identity of B the abelian group of tensor automorphisms of the identity that concretely can be described just in the following way. They are just functions that goes from the set of simple objects, the set of labels, to the complex numbers, non-zero complex numbers that satisfy the following conditions. In the vacuum, in the unit object, the value is 1. And if you do, and this happens, tau of A, tau B is equal to tau C if NB, here it should be C, sorry. Here instead of B should be C. And this is the usual, this corresponds just to the tensor automorphisms of the identity. Remember that a tensor automorphism of the identity should send, will be, in this case, automorphisms will be described just by automorphism between the simple objects. And so this scalar exactly corresponds to the automorphism associated to the simple object. And this condition corresponds to the monoidal or the tensor condition. So again, this is something in general very simple to compute once you know the fusion rules. Once you know the fusion rules, this is simple to compute. One example, it's a very general example. Suppose that you have a braided category. In this case, here I am assuming that your category is braided. So you can define for any simple object an automorphism of the identity when the scalar associated is just applied twice. Remember that here A, it's invertible, so you apply twice the braided. So at the end you get an scalar. This scalar will be exactly the number that you need in order to define. The good thing is that something that proves Jelaki-Agnieszcz, and that in the case that your category is modular, in fact, this chi define an automorphism, an isomorphism from the invertible elements of your category to the automorphisms of the identity. Yes, so there is, in this case, there is an isomorphism. So, yes. For example, in the case of SUN, here is level K, then also it's easy to compute, and this chi can be described exactly in this way. Here, this means the canonical, let's say, primitive root of the unit A to pi I, e to the 2 pi I over n. So you can compute explicitly in this case. Okay, now this braided system. So the idea is that you start with a braided category again, graded by a abelian group A. Then you also need an associative testing. So this is something that you start. And now we want to define a braiding for this associative testing. So we need a function that goes from the group A, this is the group one that you are using to grade your category, to the automorphism, the monoidal automorphisms of the identity. And also you need a function A that goes from A times A to C star that we will denote graphically in this way. So it will represent, oh, here is something that I forgot. I need here that lambda of G1, G2 should be the same as lambda of G2, G1. So the two co-cycles should be symmetric. You know, because in other case, maybe the new fusion rules could be non-abelian. I mean, the new fusion rules, it's possible that, I don't know, yes, A tensor B should be different to B tensor A. So in order to have this, you need that lambda of G1, G2 should be the same as lambda of G2, G1. And here this T represents an isomorphism from this to this. And this should satisfy the following condition. First is some compatibility between this function J and this chi that I defined in the previous slide. This is, yes. So this is in some sense some compatibility between the braid. And the other is the two conditions that will be associated with the hexagon equation. So this is one concrete, I mean, here, this box represents the lambda, the three cochange of the associative testing. This J represents this automorphism of the identity. This represents this T. And this omega, it's an abbreviation for some combinations of this lambda, this chi evaluated in this invertible object and some mix with this J. I mean, these formulas could be seen at the beginning a little complicated, but it's just in some sense a translation of the hexagon equation. I mean, in the hexagon equation of the app in the following sense. Suppose that you have an abelian group and you have a braided category that is graded by a braided, I mean, that is A graded. Then if you have one of these braided testings and you apply the associative testing to your category, defining this previously, then you can define a new braid, and the new braid is given in this way. You use the old braid, then you apply. I mean, here you have one object that is graded, I don't know, let's say by 1, and this other element that is graded by another element. So you apply the braid, and then you have to multiply by the scalar associated with the J, and also with the scalar associated with these two elements. So this is better. Oh, here is better, sorry. Yeah, so, yes.
So, Cesar, if G and T are both trivial, so that means you're not doing anything, right?
Yes, right, but this will imply some constraints, some bigger constraints over the hexagon. So in order to have this that you are saying, I mean, yeah, you will have more restrictive, more conditions over these equations.
Yeah, okay, so suppose instead of a J, T, both are trivial, just J is trivial. I map every element to the identity.
Good.
There's always a T compatible or T...
No. No, even that, no. And in the following example, we will see, but even in that case, it's not always. I mean, we have.
Okay, so I can tell you why I asked this question. So, you know, I think there's a possibility you can just reformulate this whole idea of a braided zesting as gauging instead of a 2-group symmetry, you are gauging a 3-group symmetry. And I think in the case of gauging, you map, the G has to be trivial actually. I think your G function is always the trivial function. And it's not always possible to make that happen. So, but if you go to a 3-group symmetry of a modular tensor category, and then I think you have the freedom to choose a non-trivial G. And then I think it's some version of, equivalentization of something. So anyway, that's why I ask you what happens when G is trivial and T is trivial. I think it's related to gauging in some way if these are both trivial.
Sure. I mean,
anyway, that's what I was thinking.
I completely agree with you. I mean, yes, I completely agree. I mean, what I can say is that in some sense, all these extra data again are corresponding with, let's say, trivializations of the action that naturally appear when you are gauging.
Yeah. I think there's a further generalization. I think, I consider the most general case would be, I think when you started with a 2 co-cycle, explicitly you already assume some kind of a vanishing of the H of 3 H of 3 obstruction.
Exactly.
I think you shouldn't assume that vanish. You should start with a non-trivial co-cycle in H of 3. And then I think there's a theory to do both. I think that would be the most general setup.
Yes.
So I think you should start with a H of 3 obstruction, which is non-trivial. And then you need to choose some H of 2, I don't know, some 2 cochain or something. And then I think the whole theory should all go through by choosing very complicated J and T. So I'm just saying that, gauging, we have 2 obstructions, H of 3, H of 4. Yeah, both are necessary. I think that you can work out the most general theory without assuming either to vanish. You just need to work harder. Okay, that's what I'm thinking.
Yes, we think a little bit also in that direction, but one of the things when you at the end really need to compute things is that you really, well, yes, I am not sure if yes.
Anyway, that's what I think, this could be further generalized.
Okay. So yes, this is the way to define the new braiding. And here, of course, appeared another question, natural question is, given an associative testing, when there is a braided testing, there are some obstruction theory that tell us, and this is, of course, going in the direction that Shen Han is telling me, that this should be inside of some very general theory where the obstructions naturally will appear as some higher categorical, let's say, shadow of something. And the answer is that yes, we have that there is again some cohomological theory behind of all this, controlling the existence or not. And I can explain later a little bit what is the meaning of this obstruction. So before to see the formulas, because really the formulas won't tell you too much right now, but I will in any case present them. But the idea is that you have for any element of your group some 2 co-cycle associated, and these 2 co-cycles should vanish. And also you have some, let's say, the difference of this should be also 0. So you have an extra and some additional thing. I mean, this part, it's just a 2 co-cycle with values in C star, and this A hat represent the characters. So really, even this is a symmetric character. The 2 co-cycles, again, I mean, there are concrete formulas to compute using, again, graphical notation. This is, for example, how do you compute this O1 obstruction, and how do you compute this O2 obstruction. And these formulas works in the sense that this is exactly what we used in order to compute our examples, and in particular in order to compute the case of SUN level K. But let me try to explain following the idea of Shen-Han, what is the possible meaning of this H2? The idea is when you do apply this associative testing, what you are saying, as Shen-Han said, is you are doing a different gauging. So you have a different G-cross braided tensor category associated. In this case, this is the abstraction you need to trivialize the action in the G-cross braided tensor category. So associated with every element, this is the abstraction to the action to be, let's say, trivial. But also there is another abstraction. I mean, this is the abstraction just at the level of functors. And then this is the whole abstraction at the level of monoidal functor. That's why these other things appear. So my point is that you also can give more, we didn't do in the paper, but following the idea of Shen-Han, this is exactly what is happening right now. And the good thing again is that this is something that you really can compute. So for example, again, this is a particular case of something more general that we did. I mean, again, because braided SUN level K is graded by a cycled group. But in this particular case, if you translate what these abstractions mean, happens the following. Remember that the associative systems are parameterized by couple of elements in this. I mean, by pairs A and B, when one is an integer modulo n divided the GCD of nk and n. So the testing associated with this pair admits a braided testing if and only if, and this is at the end another way to write the abstraction, but more concretely, let's say, if A, this integer, times the GCD of n and k, it's equal to epsilon plus 2b, mod n. Okay, so this is the concrete, the abstraction here, written not in terms of group cohomology, but now in terms of numbers, but this we obtain exactly from using group cohomology, this part. And now if the abstraction vanishes, so if this equality holds, then there exists n different braided testing associated with the, I mean, associated with this fixed associative testing, parameterized by complex numbers that satisfy that tau to the n is exactly this number. And in this case, this j, it's trivial. You can take as a trivial, this j that, and this t is just tau to the minus ij, where this is the, I mean, yes. And also one of the things that we did even in more general, with more generality, is to compute explicitly the new, I mean, because in this case, these categories that you get, all of them are again modular. So one natural question is, what is the modular data of these new modular categories? And the modular data can be written explicitly in terms of the old modular data, and just you change by some numbers that are given by this formula. Here, this is the grading of your simple object. So in terms of Young diagrams, is the number of boxes mod n. And oh, here, yeah, and here similarly, it's the old t, and just you have to multiply by this particular number.
The only thing strange about this formula is the minus sign. Must be a convention. So yeah, the coefficient for theta should be just the diagonal s, with a 1/2. But somehow you got a minus sign, which means your convention of theta is in some other way. Anyway, I think the formula makes sense.
For example, for SUN levels, SU3 here should be 3 and 3. Oh, I'm sorry. So here, braided testing of SU3 level 3. This is one of the examples that we work out with a lot of detail. So the associative testings, we know, I mean, in this case, the GCD, in case of 3-3, will be just 1. So the associative testings corresponds to 2 pairs of numbers set 3 times set 3. In particular, if you take the associative testings corresponding to 1 and B, the fusion rules, the new fusion rules are completely different. So for example, the fusion graph of SU3 level 3 is this one. And the new fusion graph is this one. Because one of the things that happen is that in particular, the standard representation, when you do in the usual SU3 level 3, when you do 3 times the standard representation, you have a copy of the trivial representation inside. So in some sense, let's say the order of the standard representation, it's 3. But when you test using this, now the new standard representation, the order is bigger. I think it's, if I remember correctly, is 9. So one of the things that happen is that it doesn't, I mean, if you apply for the new standard representation 3 times, the trivial object is not inside. And among the associative testings, because here we have 3 different associative testings, only 1, 2 admits upgrading. The other 2 doesn't. Okay, so for the other 2, it's not possible to solve the pentagon equation, the hexagon equation. For that particular case, we compute this is the new S matrix. Of course, the new S matrix looks really different in some sense, because of course the modular data, it's associated with the fusion rules, so would be different. Perhaps doesn't have too much sense to present explicitly what it is, but look at here, remember that we have a set 3 grading, so here the simple objects will be decomposed in 3 parts. So the idea is that this A, B, and B won't change, but the C and the D will change. So we explicitly compute the fusion rules. Here's theta, I don't remember, it's a root of I don't remember the order. But yeah, but we have concrete formulas for both, yes. And we explicitly compute the new fusion rules and everything for this particular case, and also for other cases, like SU4 level 4. But it's a little bigger, of course. Now I think the rank is 35 in that case. This case the rank is 10, so it's something that you can at least write in the paper, but the other case is more complicated. Let me also, as an example, talk something that we did some years ago in a paper with Paul Bouliard, Tobias Hage, Richard, Julia, Eric, and Chen Han. In this paper, we studied, this paper, in some sense, was the first time where zesting appeared and where we add the number of zesting. So in this case, we wanted to construct from a supermolar category the other, we know that associated with a supermolar category, there are other supermolar categories very close related. I don't want to explain with all the details, but the thing is, using zesting, in this case, we use zesting for the case of cyclic group of order 2, only for that case. So in that particular case, the obstruction doesn't appear. So we just present a method to construct new spin modular categories as follows. So the idea is that a spin modular category will be a modular category with a fermion. Yeah, when for a fermion I mean a let's say, a copy of super Beck inside of C. So it's a F such that tensor F is equal to trivial identity, and such that the braiding it's minus the identity. And for every spin modular category, you have a set to gradient, where let's say the objects in the trivial component corresponds to the objects that are transparent with respect to the fermion, and the objects that are in the component 1 are those who the double braiding it's minus the identity. Yes. So in this case, you can define explicitly a braided system where that takes value exactly on this F. In this way, lambda of 1 is equal to F, and lambda of 1, 1, 1 is equal to I. And you can apply, I mean, you can zest and again apply the zest to the zest, and you can apply several times. At the end, you get a different. That's I mean, if you apply several times to the new gauge again, because when you apply this gauging, the new fusion category that you obtain is again spin modular, then you can apply again and you can apply again, and then you get a different. And we knew from this paper that they were different because the central charge changed exactly for some eighth root of the unit in this particular case. So this was, in some sense, one of the things that inspired the notion of zesting, and when we talk about zesting for first time.
So in this case, the zesting would increase or decrease central charge by 1. Is that right?
It depends what kind of. I mean, I'm referring to the multiplicative central charge. So in this case, if I remember correct,
no, 1. That means the C. So what about the C? Does C increase by 1 or decrease by 1, the central charge?
Which means the eighth root of unity for multiplicative.
Yes, I mean exactly.
Eighth root. Yeah, eighth root. Is that eighth root? Okay, yeah. But can you get the something? We know there's also a change to make C change by 1/2. I mean 16 root. It does. So that's not zesting then.
We couldn't do that by zesting.
Okay. Yeah.
We only get 8 out of 16.
Exactly.
Okay. That's also a billing group. Okay. Thank you.
That's more serious.
Okay. So more quickly, one other question that we studied: what happened with the new braid group representation? So the thing is, in this case, it's easy. We wrote a concrete algebra automorphism between this algebra. I mean, if you take one simple object graded by, let's say, A, there is a concrete algebra automorphism between this and this, given by this formula. And the point is that the new braid representation changed very few. I mean, assume for a moment, I mean, what I'm saying is, if you take one of the generators of the braid group and you see what is the image through this new braid representation up to the automorphism, this is the this is the image through the automorphism. It's just the old one times one scalar, and the scalar is associated with this T and with this G, but it's just one scalar, and this scalar in general is a root of the unit. So, for example, if a premodular category has property F, that means that the image of the braid group is finite. Again, every possible zesting again will have property F. So in some sense, you cannot move from something that has, let's say, finite image to something that doesn't have using this procedure. Yeah. And this is also it was one of our motivations to study this notion of zesting, because we know some concrete examples of fusion categories, modular categories that have property F, and we know other that in principle it was not completely clear that they have property F, but it was clear that they can be constructed using zesting. So now we know that exactly those also have property F. There are more results in the paper, but yeah, I think I am over time already. So we explicitly give formulas for the new S and T matrix in very general terms. And as I said, we also classified cyclic zesting very concretely, I mean, with formulas for everything. And thank you very much for your time.
Thanks, Cesar.
Thank you very much.
Thanks, Cesar.
Yeah, I have a question.
Go ahead.
So the suppose your lambda, this pointed, this invertible object, is kind of transparent to everything else, just like identity. You know, like this Fermion case. The Fermion case, your lambda taking the value on the invertible object, which is transparent to everything else. But in general, let me see.
Well, in the Fermion case, not necessarily is transparent with everything. In this case, I mean, but because in this case, it will be transparent just with the things in the trivial component.
In the trivial component, I see.
Yes, in the other component won't be. But let me say something that perhaps go in what you are, and we move from something that is not modular to something that is modular.
Okay.
Using braided testing. But for the case of SUN level K, we know that everything will still be modular, and we change. But we know examples where this property can change. Even in some very, very extreme cases, we can go from something that is symmetric to something that is modular. But it's very,
so actually, I'm thinking about, for the Fermion example, the central charge is changing by 1. This kind of zesting have a physical interpretation is as a onion condensation. You know, we interpret this as a condensing this fermion, making this fermion form of quantum Hall states, then you're changing central charge by 1, and that seems correspond to this zesting. So this make a suggestion or some hint whether in general zesting have this property or not. That is whether this zesting and this condensation of this abelian anion, whether there's can be a relation. Because like this, for this Fermion example, is we understand this zesting can be interpreted as some kind of this abelian anion condensation. There's a hierarchy construct in physics. But I wonder whether in general, in the previous case, more general case, whether this is true. Another one to try to say that whether this zesting would only change the central charge by 1. Seems in general can be more general, right? The zesting may not change the central charge by, let's say, by root of eighth root unity. The central charge can be modified more generally, looks like.
You know, I'm guessing they are the same. You know, we heard these two talk, Lantian and the Zesting. I think they are the same thing. If I remember correctly, Lantian cannot change the central charge by 1/2 either, right? It has to be.
No, it cannot,
So I believe they are the same thing. I think these two topics are the same in the most general setting.
I see. That'd be really interesting.
Yeah, I think what it is, I think it's still I think it's a hierarchy construction at the most general zesting is that, gauging in a sense is that, we are just, used to old thinking, which is we want a group action on modular tensor category.
Yeah.
What it really should be is not a group action, should be a WAC-G action, which is a abelian modular tensor category. If you take a modular tensor category point of view of a finite group, that will kill the first obstruction. There won't be symmetry fractionalization. So the H/3 obstruction completely gone. And that's lifting the categorical number by 1. And I think that's what I think I said at the very beginning, when I was asking. So that's the first thing. You choose the H/2 related to this action. And then H/4 can also be trivialized by thinking this as, a 3+1 theory. So I think it should all go through as SPT in 3+1 setting. So I think they are the same in the end, should be.
So you mean there's some more general setup such that this zesting and this anion condensation
are the
It will
same.
be the special case of this more general setup.
Yeah. This more general gauging, which no obstruction at all. You can always do it.
Okay. Okay.
Maybe a little bit H alpha 4. I'm not 100%, but definitely H alpha 3 should be gone.
I see.
Yes, one of the questions that we have, in fact, is the physical interpretation of testing. We are not completely sure what this interpretation is, I think.
I think the best is to make this the same as a Lantian's talk as annual condensation, which I was completely confused so far by these two things. I always consider condensation and gauging opposite to each other. Apparently, they are not so. I think there's a way to think them exactly the same, which I don't know what to do.
I see. But the zesting, repeat my question. The zesting may not change the central charge by eighth root unity. It can be more general. Is that right?
Yes, it's right. It's
okay.
Right. Exactly. I mean, in this case, in the case of supermodular, I mean, the point in some sense is that in the case of cyclic group of order 2, you need the following. In order to apply to get an associative testing, you need a square root of -1. And then in order to find an braided testing, you need again a square root of the previous one. And then in order to get a ribbon, then you need another root of the unit. But when your group is cyclic of bigger order, in this case, it's more or less the same, but now not with skew root, but roots of order n, let's say. So I think that central charge could change differently if you change your group.
No, I don't necessarily agree. If I hear you correctly, so I think I agree with the Xiao-Gang. Let's not talk about multiplic central charge. Let's talk about the real central charge, define mod 8.
Yes.
Are you saying you can change this by 1/2, 1/4, or 1/8?
No.
You can only change by integer.
No. I'm not saying that. I'm saying that in the
case change by integer.
In the case of supermodular, we have a very concrete formula of how it changed, because exactly it's a cyclic group. But in the other cases, in principle, it can change differently. That's the only thing that I am saying.
But the change always integer. They always can only be changed by integer. Is that right?
That's my belief. That's my belief. He can change ST matrix by any root of unity, but I don't think he can change the central charge beyond the integer. That's what I think.
I see.
Because if you can, that is very important clue. Because if central charge only changed by integer, then this anion condensation and that may even be equivalent.
Yeah, that's what I believe they are. If you formulate both correctly, they are the same thing. That's what I believe.
That would be amazing.
Yeah.
So actually, one can compare, because for the anion condensation, there is a formula how ST matrix changes, and you also have a formula. And by comparing these two formulas, one probably can have some clue. Yeah, what's going on.
But I think the condensation is more general at this point, because his change of ST, it seemed pretty simple. It's basically like a tensor 2 theory together. One is abelian, the other is not abelian.
Oh, I see.
But I think in the end, if you think about if you think about condensation, so you are not doing the most general either. In principle, you can condense, any anions, not even abelian ones.
Not abelian is much more hard.
I know, but when you do condensation so far, you can also condense bosonic objects. They not necessarily has to be abelian.
Yeah.
So that suggests condensation can be more general. So, but now what you are doing is condensing abelian anions.
Yeah, we're condensing invertible object.
Yeah, that's actually what you are generalized is just instead of a +1 -1, you generalize to any root of unity.
Yeah.
But then you can only change the central charge by integer.
Yeah, exactly.
And here I think the formulation he using is not the most general. He can also, I believe, only change the central charge by integer. He cannot do like 1/2. which you have to stack in icing or something.
Okay.
So I think there should be a formulation. Those two things is, in my kind of a picture, you have these three things. You have a modular tensor category with a group action. You have the one which is after gauging this G cross. I think you should start off from the G cross, and then both theories should be unified there.
I see.
And then you go one direction to another one, the other go maybe another one. So, but anyway, so I think that should be the relation between the two. And as you said, the most important hint is that you change the central charge by integers.
Yeah, that's right.
But maybe I inject a little bit. So I remember the paper of Lan Tian and Xiao-Gang and Kong Liang about this tensor product. They actually tensor of this central charge group. So basically, they tensor the whole thing by a icing over the symmetric category Z super vector space. So that's like how they get the half central charge.
I think that's a different paper.
Yeah. The paper with Kong Liang and
that's a different paper. But
I think this is supposed to be a tensor product over a symmetric category. Then you get the half.
Yeah. That's go beyond both this framework.
Yeah, that's a modular expansion.
You get the, if you do the integral one, you get the integral central charge.
Yeah.
So Xiao-Gang, when you mention anion condensation, this changes the dimension of the category in your setting, or it doesn't have to? The global dimension.
Oh,
global
yes.
dimension.
There's a capital D, right? Yes, it's changing that.
Yeah.
It's about changing in a very simple way. It's like by multiplied by some
by a rational number.
Some number. Yes.
You can bigger or smaller. Depends on.
Yeah. In some very
we don't change. Yeah, we don't change. Don't change the dimension. Even with the quantum dimension of the objects doesn't change. Something interesting.
That's true. In our case, the quantum dimension do not change. But because we are talking about a modular tensor category, so we always map one modular tensor category to another modular tensor category. So we do this completion. So total quantum dimension changes because we go from modular tensor category to a new modular tensor category. So there's some certain completion in it.
Well, I think the difference is, Zesting is not as general as, condensation yet. The condensation is that you take all the quantum dimensions, you're entitled to change the multiplicity of the quantum dimension, but as a set of the number, they are the same.
Yes, that's right.
I think Zesting is more restrictive. They even don't change the multiplicity, I believe.
I see. But on the other hand, after Zesting, you may not get a modular tensor category, right?
Well, there are formulas for you to check which are modular, which are not modular. So
yes, okay. But what I try to say is that if it's not modular, you can maybe add more things to make it.
Well, that's a good idea. That's actually true. Yeah. Maybe it's just a defect. You want to you want to double or triple certain objects.
Yeah.
To make it
then it become modular.
Make it modular.
Yeah.
You should just do an inflation or I don't know.
Inflation include inside of the center if you want, and this is smaller. Of course, this is a little silly, but this is something that you always can do for any braided category.
Well, yeah, I think the idea Xiao-Gang is suggesting is that you look at the if you have a spherical. Actually, I want to ask you the question first. Does Zesting preserve unitarity?
Yes. I mean, this is we do. I mean, the thing. Yeah.
So here's what Xiao-Gang is suggesting. So you do your things, and you realize, oh, gee, I don't get a modular tensor category. I get a pre-modular tensor category. So what goes wrong? And a certain column of the S matrix become the same column. Mm-hmm. And then Xiao-Gang would say, okay, let's try to do some further twisting so that they will become different. Mm-hmm. And that would, maybe you need to add another column or something, but the same column. And then you do a little bit of changing to make this into an invertible matrix, and that will become modular again. So what Xiao-Gang is saying that you do a construction, you get some of them modular and some of them not modular. But those who are not modular can be fixed by take the degeneracy, and either you change some of them, or maybe you need to add another column or delete a column or something. So there's a process for you to go from those which are properly pre-modular to modular, suggested by hierarchy or condensation variance.
Yeah, the condensation construction have some kind of a guide. So what is a new onion content? How to get all of them? There's from wave function, there's some hint how to get all of them. Yeah, that's
my guess is the following. It's a very easy construction. So you take their zesting and you discover, oh, terrible. It's not a modular tensor category. I get 3 columns exactly the same in the S matrix. And then what you say is, oh, the 3 columns are related by some anion acting on them. So let's condense that anion.
Yeah.
And then the 3 columns become 1 column. That turns out to be a good S matrix. And now you get a modular tensor category.
Maybe, I don't know. Yeah. But so it's quite amazing. Yeah. Okay.
Very good. So if there's no more questions, let's just thank Cesar again. And I will stop